and welcome back to another episode of Amiga game programming series. We spent most of previous episodes setting up all the groundwork for level rendering. We allocated memory we'll use for drawing the level, and then spent considerable amount of time initializing Amiga hardware chips to use it. During the process, we learned more about copper and playfield hardware. And today, we'll build upon that work and actually get the tiles we rendered way back in episode 2 on screen. Rendering tiles is basically copying squares from source to screen. And Blitter is perfect match for that. Blitter is another coprocessor on Amiga, like copper. It can copy rectangular blocks of memory and draw lines. And it can do that really fast. Memory copy is about twice as fast as with 68,000, and it can draw lines at almost million pixels per second. So, quite fast. There's usually lots of wrestling until I get it to perform stuff the way I want. And it wasn't any different this time. But I want to spare you with all the details, so I'll show you the progress in emulator and then go through working code at the end. There were three main things causing the issues: calculating correct offset into tile set for any given tile, updating source and destination pointers, and properly setting up Blitter to do work as I wanted. And as you may have guessed, all had to be arranged exactly right in order to yield expected results. And sometimes during the process it was actually challenging to figure out which one of them was off. So there was quite a bit of repetitions and debugging sessions. But at the end I finally figured it all out, and here's the result. Majestic, if I may say so myself. It's so nice when you see the results of your hard work finally come together. And as promised, let's check the code that runs this. But first, let's quickly check level data to get an idea of the structure. This is the definition of our level. So here is level data and all 4 layers. So background and then coming up to foreground. This also simplifies rendering because we can just start at this tile and then just move on down until we reach the end. Okay, and now of course for the main treat, the code that renders the level. So first of all, we need to clear the bit planes. We need to read the values from the data, so these values here, and we point 80 to the start of that data. So 80 points to exactly this byte. Similarly, we also need to know how many layers we need to draw. So we have 4 layers, we need to subtract 1, and D6 is our counter for all the layers. And then we can start the loop for the layers. For each layer, we need to point destination to the start of window bit plane pointer. So this is what this line does. E05 is our pointer, and in D5 we have the counter for our tiles. And then we start rendering the tiles. First of all, we read tile index from tile data. So 80 points to our tile data, we read it and advance it by 1 byte, because this is byte operation, byte move. And so afterwards, lower byte of D0 holds the index of our tile. So if you go here, we read this byte, and then the 80 pointer is advanced to start of next tile index. And then we compare it with 0. Tile index 0 represents fully transparent tile, so we don't have to render at all, we just skip to next tile. And if it's not 0, then we need to render the tile. So how do we do that? First of all, we store the pointer to tile set image in A4 register and to mask image to A3 register. So A4 points to exactly this pixel and A3 points to this pixel of the mask image. Then we need to calculate the offset into both mask and tile set images based on tile index that we just read in D0. So if we have tile index 11, which is this tile here, we have 10 tiles in the row. So to calculate its y coordinate, we need to divide the tile index 11 by 10. And whatever is the integer result is our y coordinate. So in this case, it would be 1. And the remainder of this division, which is also 1 in this case, is our x coordinate. And this is exactly what we do here. So we need to divide D0, which is our index of tile, by number of tiles per row, which is 10. So whatever is here divided by 10. And the result of division is D0 register, the upper word contains the remainder, and the bottom word contains the result, the integer result of the division. Basically, upper word contains x coordinate and bottom word contains y coordinate of our tile inside the tile set image. All that we need to do is copy both values out. So D1 is our y coordinate and D0 is x coordinate of the tile inside tile set image. Okay, so now that we have the x and y coordinate of the tile inside the tile set, we need to calculate the byte offset inside both images, tile set image and tile set mask image. And here is the formula I came to: row multiplied by tile height multiplied by number of bytes per each tile set row multiplied by number of bit planes, because we need to skip all 4 bit planes. And then we need to also add the column. And column is a bit simpler, it's just the index of the column multiplied by number of bytes per tile. So this is what this part basically does. So A3 and A4 point to the start of mask and tile set images. We need to increment that by this amount we calculated here. So we need to add this part, and then we need to add this part. And this is what we do here. So at this point, A3 points exactly to the first pixel of the tile. So it points exactly here. And for mask, it points to its mask. Here. You might be wondering why we use the same offset for mask as for the image. After all, mask is just 1 bit, it's on or off, while our image has 4 bit planes, 4 bits per each pixel. And this also caught me unprepared. I'll show you. I think this will make it quite clear. This is our mask image, and this is how the mask image looks like. And let's just change this a little bit. So each tile has 16 bits for width. And so let's group, so that is 2 bytes. So this is one tile, this is next tile. It's like this line, and this part is next 16 pixels, and this part is next 16 pixels. So next tile, and so on. And let's make the width 20, so we have 10 tiles. And this is exactly representation of this image. This is the result of IFF converter. So this is not IFF image, this is raw bit plane data. And as soon as I saw this in hex editor, it immediately became clear. So let's look at it. This is the first line. It's this line here. So first of all, the first 16 bits are all zeros. And yes, they are all zeros as is seen here. Next, 16 bits, first byte, first 8 bits are all full, so we expect FF, and we have an FF here. And then the next byte, next part of the tile has some transparent pixels, so it's not all bits on. And it is like that. And similarly for next and next and next tile, this line, it makes sense. So let's take a look at the next line. Next pixel line, like this one. Again, we have all zeros, and we have all zeros here as well. And then for next tile, the whole tile is full, and next tile is full, and next tile is also completely full. So we expect 2-3 tiles to have just FFFF. But here actually it repeats the same thing. This line is repeated again and is repeated again and again. It's repeated 4 times. It's only in 5th line that we have the data that we expect to see in 2nd pixel line of tileset mask. But this one is also repeated 4 times. So what actually happened, I think when I was exporting from IFF converter, I didn't set the number of bit planes to 1. It remained at 4, the same as for image I exported previously. And therefore it exported each line 4 times. So it's not really optimal, but it's okay for now. We are not really memory constrained, and I don't think we will ever be for this little game. But if you were, we would need to re-export this and adjust the code. And who knows, perhaps we will do that in the future. Right, now we have everything prepared. All the pointers are pointing to correct sources and destinations, so we need to bleed. And how do we do that? Well, Blitter is composed of several registers that we need to set. And after we set all of those registers, then we set also bleed size, and setting bleed size will actually cause the Blitter to run. But before we execute Blitter, we need to take care to wait until the current Blitter operation stops. So this is what this subroutine does, and we will look at it later. For now, just keep in mind that we need to wait for it. Next step is setting up Blitter control registers. And I prepared a macro. I think it's the first time I'm using macros in this series, so in this case it's just one move L, but the whole point of this macro is to split the long word into 4 distinct bytes, so it's a little bit more manageable. And if we return back down to usage, and it's quite simple. First we write the name of the macro and then we supply all required parameters. But before going really into how this bleeding is set up here, let's just spend a couple words about Blitter. In a nutshell, Blitter copies data from one part to the other. We have 3 sources and 1 destination, which are called A, B, C, and D. And in our case, all 4 DMA memory pointers are present. Next byte, we define the operation, how the source will be copied to destination. In our case, it's 11001010. What does that mean? A source is our mask image, B source is our tileset image, C source is destination, and D is also our destination. And this is how it combines. If bit in mask is 0 and bit in source is 0 and bit in destination is 0, then we don't write anything at this location. If mask is 0 and source is 0, but we have something on destination, we write 1 to destination. And so on. This is how to interpret this table. For control word 1, we don't need anything, so we leave everything to 0. Next step, we specify the mask. In our case, we set all the bits to 1 because we want to write everything. Right. Next up, we need to tell it all the source and destination pointers. Next thing, we need to tell it the modulo for each of the sources and destinations. If we go back to our hex editor, I think it will be easier to explain here. Let's take, for example, that we are copying this tile, 2nd tile. So when we start, the pointer we set points here to the start of the data for the tile. What happens after the bleed? This register will be updated to point to the end of this data. Blitter actually changes its registers. Blitter rendered this line of data to destination. So this is just 1 bit plane. We need to tell it how far it needs to fetch into memory to reach next bit plane data. We need to have it point to this location because this is next bit plane data. We just need to add the whole width and then subtract 1 tile. And this is what this code does. And for the destination, it's quite similar, except we need to pass the whole window bit plane row size. The only thing remaining is to bleed. Blitter's size register is a little bit hard to deal with because of, so to speak, interleaved data. So what do I mean by that? Lower 6 bits specify the width of the blit, and upper 10 specify the height. But it's a little bit easier to think of it in terms that we need to shift height by 6 bits to the left, and then we just need to add the width and we're done. The same thing is done by multiplying by 64. So shift left 6 or multiply by 64 is the same thing. And you might be thinking, well, isn't shifting much faster operation? And yes, of course, it's much faster, but this is not calculated in runtime. This is calculated during assembling process. So if you look at the binary, it will be fixed number here. For each tile is 16 pixels, and each pixel is represented by 4 bit planes. That's how many rows Blitter needs to copy from source to destination. And then we add the width. And another complication here is that width needs to be specified in words, not bytes. And this will cause Blitter to blit. And while it is blitting, we can update our pointers to point to next tile. First of all, we update our destination screen pointer, where we are drawing to by 1 tile. That's 2 bytes. And then we compare if we reach the end of the line. And we do that by incrementing D4, which is our tile counter, and compare it with as many tiles as we have, 20 in our case. If we didn't, we can continue with next tile, which we'll see afterwards. But if we did, we need to update pointer so that we can start rendering in the next line as far as tiles go. And to do that, you can check this chart here. When we finish drawing the line, we are pointing at this location here. And we need to jump all these bit planes, so we point to the first bit plane of next tile row. And that is exactly number of bytes that each bit plane row takes, multiplied by number of bit planes and multiplied by tile height. After we add that to destination, it points to this place here, so we also need to move it to the start of the line. So we just subtract 1 bit plane byte row. Afterwards, we are done and we can clear D4, our pointer for number of tiles in X coordinate. So it's prepared for next loop. Then we proceed to next tile, and that means decrementing our tiles counter, and when it wraps below 0, we know that we are done with layer. And the last thing remaining is to check if we are done with all layers, which means decrementing D6, our layer counter, and when it wraps below 0, it means we are done drawing all the layers, and we can finish. And as promised, we will also take a look at wait blitter. It's quite simple subroutine. We simply test bit 6 of DMA control and blitter status read register. And if we look at description, bit 6 means blitter DMA enable. As long as this bit is set to 1, it means blitter is doing its job. When it's 0, blitter is inactive. And we stay in a loop, reading continuously the bit until it becomes 0, and then we jump out and return. And that's all there is to it. There's not so much code, but it can be tricky to set up. I only showed you the most important part here, but if you are interested in the rest of it, you can become my patron. As gold patron, you get access to full source code. If that is something that would interest you, see the link in the description below. As the last thing, I wanted to convert level data from textual to binary form. Textual representation made it simple to develop the code, but it's not easily manageable, especially if we'll want to use multiple levels in the future. Of course, we first need to export the data into binary form from Promotion. I tried several supported formats and decided to go with GBA tilemap at the end. It made most sense data-wise. So now that we have our data, we have to adapt the program to use it. First of all, we have to include all layers which now only takes 4 ink bin instructions. While importing binary data, I got an idea of better managing various data imports. We need to import various pieces of data in our program. Images and level definitions at this point, but there will be more in the future. On Amiga, we have 2 types of memory, cheap and fast. Regardless of total memory, there can only be 512 kilobytes of cheap RAM, so I always think of it of being more at premium. While it shouldn't matter for our little game, it's good practice to think of this already at this point. It will make our job simpler should we hit the limits down the road. So we have to decide which part belongs where. It may sound complicated, but it's quite simple. You see, custom chips, copper, blitter, etc. can only access chip memory. So all data that needs to be visible to them needs to be stored there. In our case, that's our image and mask data. The rest can go to fast RAM. While here, I also want to move all data imports into data folder. They are not routines after all. First, move our data file and rename it into fast. We'll use it to store all data for fast memory. At present, it only contains level data. Then I want to repurpose images.s into chip.s. This file will contain all chip memory data. And of course, we have to adjust our import statements in main.s. Oh, forgot about copper list. This also needs to be saved into chip memory, but I want to keep it separate from other data. By the way, we use section directive to specify the type of memory we want the following content to go to. It's assumed fast unless specified differently. The only catch is all data and code following this directive will be saved to corresponding memory. So to ensure we don't accidentally start writing into chip memory, we include chip memory files at the bottom of our include statements. Right, back to code. GBA file starts with 2 double words specifying number of tiles in X and Y directions. But we'll ignore that for now and continue to use our hard-coded constants. We might revisit this in the future. The other change is that our tile indexes now take 1 word instead of 1 byte, so we have to update tile reading code to compensate. And then we also need to swap bytes. GBA file is saved in little endian, meaning low byte is saved before high byte, but 68,000 is big endian, so we need to convert it. I chose to shift right 8 bits for now, so this code is not really converting endianness. But we will have far less than 255 tiles, so we don't need the upper byte. And that's all there is to it. Here's old code on the right for comparison. Okay, but let's run this to see if it actually works. It does! All that remains is to commit changes to Git and push to GitHub. And that's also the end. In next episode, we'll start working with sprites. Thanks for watching. Until next time, goodbye.